Okay, so we spent $10 billion on the James Webb Space Telescope, and it's been operational for a couple of years now. So that begs the question, what have we actually learned? Well, in some sense, the purpose of the James Webb Space Telescope is to study the universe and our origins. That's the simplest, most fundamental version of what James Webb is trying to discover. But in some sense, that's what humanity has been trying to do for thousands of years. For eons, humans have been sharing the same sky, studying it, trying to figure out where we came from. So, in order to really appreciate where James Webb has come from and where it will continue to go, I suggest we do a little bit of time travel. So, if we were to travel in both time and space to Italy 2,500 years ago and look up at the night sky, we would see the night sky that Pythagoras looked at. Now, we might not know who Pythagoras is, but you certainly know his most famous theorem. That is the Pythagorean theorem. Now, we might have some math trauma associated with this theorem back in grade school, but there's one defense that nobody taught you in school. That was that Pythagoras is deathly afraid of beans. He actually believed that the souls of past humans were contained within beans, so he avoided eating them at all costs. He was also a cult leader. So, anyways, even though our guy was a cult leader, he was actually very, very clever. He and his math fraternity friends all came up with a very, very interesting idea known as the harmony of the spheres. So he and his friends looked up at the sky and they noticed patterns. What this meant was that mathematics had started to become a reflection of reality. You could actually use math to look at the sky and predict how things occur. Now, the Pythagoreans were also very clever in the sense that they combined the arts and the sciences. So while they studied math, they also studied music, and they noticed the intrinsic connection between the two. What this meant is that the math of the motions of the celestial bodies reflected to harmonies. They converted directly to music and sound. Now, this is quite interesting, and it might seem a little bit strange, but this was the first time ever that mathematics had started to become a reflection of reality. And this transitioned on to Plato and Aristotle to come, who would really take this idea forward into the scientists of the future. Okay, so this is where humanity started to overcome the dogma of Plato and Aristotle to start to get a little bit closer to what we would call the capital T truth. This is where we leave the realm of natural philosophy and start to enter into the realm of science. So over the next 2,000 years between Plato, Aristotle, and the sort of medieval period after that, you then enter into the era of Galileo and Kepler. Now, Galileo and Kepler had the same sky that Plato, Aristotle, Pythagoras, the Buddha, everyone before them had. The sky changes, it just changes very slowly. So, they had the same sky, but they had tools that could help them magnify what they saw in the sky and get a closer representation of what's actually out there. Now, this is where people like Galileo started to see that the heavens aren't perfect, like Plato had said. So, tools make all the difference in astronomy. Even though astronomy is the oldest science, it's been around for thousands of years, it really didn't take off until the invention of telescopes. And that's because astronomy is a unique science in the sense that it's observation rather than experiment-based, for the most part. So, what astronomers do is they spend a lot of time and money developing and creating tools to look up and further back into the universe. Up until very, very recently, we used only telescopes here on Earth. But that all changed when we realized that you can put telescopes up in space and they act a lot differently. They're much more clear. There are so many benefits with putting telescopes and observatories up in space, but that comes with its own downsides as well. So that's what we're going to look at next. So getting things into space is risky and expensive. It's expensive, especially if getting it into space doesn't work. If it doesn't work, that means the rocket blew up and you lost decades of research and development and production. So it begs the question, why would we even want to bring these things to space in the first place? Well, it all really boils down to two things, and they're very closely related. That is light and our atmosphere. So our atmosphere is a beautiful thing. It's what we breathe. It's made up of mostly nitrogen and oxygen. It's great. We want it. If we didn't have it, we would look a lot like Mercury or the moon. So, atmospheric disturbance is one reason why we might want to invest in that risk and that extra expense to leave Earth's atmosphere and do observation from space. But one other crucial reason that we want to leave Earth's atmosphere is light. Now, this might sound strange because we clearly have a lot of light penetrating our atmosphere and getting to our eyes. But our eyes are tuned to see the light that actually can make it through our atmosphere. We don't see all of the light. Some of the most important wavelengths of light that are a part of the electromagnetic spectrum can't make it through our atmosphere. These include things like UV, X-ray, and most importantly, arguably, infrared light. Now, infrared light is what James Webb observes, and there are some crucial reasons why we might want to get up into space so that we can see the universe in this certain wavelength of light. James Webb observes in infrared light, but like I said, light isn't the only reason that we might want to go to space to observe things. The first major space telescope was Hubble in 1990, and Hubble actually observes in the light that our eyes can see. It observes in optical light. Now, it uses a 4.5 meter squared mirror that was absolutely ginormous at the time. It was designed to be repairable and serviceable by astronauts because it's relatively close to Earth. In fact, if you were to tip Colorado on its side lengthwise, that's how high up Hubble orbits. So, when Hubble was first deployed, it actually had an issue with one of its mirrors. It was out of focus. And so, we were able to send astronauts up there to actually fix it, which is remarkable. But Hubble absolutely changed astronomy forever. For the first time ever, we had a giant mirror up in space to take high-resolution images of things without any atmospheric disturbance. We were up in space looking at space. So, Hubble was launched in 1990, and soon after that, it was used for a fairly controversial reason. Astronomers from all over the world were dying to use Hubble. It was this brand new, fancy, super expensive space telescope, and people wanted to use it. So, it was very controversial when a group of astronomers used it to stare at a black part of the sky. They spent 11 days straight using Hubble's massive mirror to look at a part of the sky where they didn't know if they would actually find anything. They wanted to use this new light-gathering ability to stare at a part of the sky where no light had previously been observed. What they discovered after looking at that black part of the sky for 11 days straight was breathtaking. Okay, so I laid down in a cactus earlier, but that's okay because that image that I just showed you is called the Hubble Deep Field, and it absolutely revolutionized astronomy forever. It was crazy how far back we could see with this new revolutionary image. But what's even more revolutionary and remarkable is that what it took Hubble to do, how do you word that? What it took Hubble to do, Hubble took 10 days to do, how do I word it there? But what's even more remarkable is that what it took, that sounds like fake English. So what's even more remarkable than the Hubble Deep Field is that what it took Hubble 10 days to accomplish, it took the James Webb Space Telescope only 10 hours. Now, what Hubble discovered was that darkness does not imply emptiness. When we look up at the sky and we see dark patches, that does not mean that there's nothing there. Hubble introduced this. James Webb took it to the extreme with its own deep field image. So the deep field image from James Webb was one of the first images that was ever released by James Webb. Any astronomy nerd will tell you that they know exactly when and where they were when that image was released. Now, this is pretty remarkable. There was a lot that was shown in this first image. It showed two remarkable things that explain why James Webb observes in infrared light. The first one is gravitational lensing. We were literally able to see the curvature of light from galaxies caused by the mass of other galaxy clusters. You can see that in the image, I'll point to it. Now, the other thing that we can see is redshift. This is literally the stretching of light caused by the expansion of the universe itself. This is part of why James Webb observes in infrared light. We need to be able to see those longer wavelengths that have been stretched out by the expansion of the universe itself. Now, that's why we need that 25-meter squared mirror. It's absolutely ginormous. You can actually see it on the back of my laptop here. This is what the James Webb mirror looks like. Now, this ridiculous mirror that you can see on my laptop here can capture quite a lot of light. In fact, if you were to put a kid's nightlight on the surface of the moon and looked at it from Earth, James Webb would be able to observe 1/20th that amount of light. To produce that amazing deep field image, JWST needed more than just a giant mirror. It needed some very strategic placement in space as well. Now, that's a question you might not think about. Where do you actually put a space telescope in space? Well, there's a lot of thought that goes into it. There was a reason that Hubble was so close to the Earth. They wanted it to be repairable by astronauts, as I discussed earlier. James Webb does not have that same luxury. JWST is located 1.5 million kilometers from Earth. That's about 1 million miles. Now, when you add that many zeros to a number, it starts to become meaningless to us humans. So to put that into perspective, that is 4 times farther from the Earth than the moon. If something goes wrong out there, you can't fix it. So the pros of putting it out that far must outweigh the cons. What are those pros? It's out there because it's at a point called L2. This is a Lagrange point. At this point, gravity from the sun and the Earth balance out. So it's a very, very stable orbit. It allows for continuous observation out into space as well as continuous communication with the Earth. Now, there's one other reason that it's out there that's crucial. It is able to block itself from the heat of the sun. That orbit allows for a stable thermal environment. This might not seem like a big deal, but James Webb observes in infrared light. Infrared light is the light of heat. Anything that emits heat, anything that's hotter than 0 Kelvin emits infrared light. That includes our bodies, the Earth, the sun, any nearby asteroids or comets. So in order to focus on the correct infrared light, James Webb needs to be able to block out everything else. Okay, so that might have seemed like a lot of background for a video about the James Webb Space Telescope, but there's a reason that I started with Pythagoras, built us up from Kepler and Galileo all the way up to the present with the Hubble Space Telescope and James Webb. Now we're going to transition into the next part where we actually look at some of these discoveries. But those discoveries are going to mean so much more now that we've explored the origin of that discovery. Okay, this is where we've started. This is the James Webb Space Telescope deep field image. We see a galaxy cluster here in the center. We see some gravitational lensing of galaxies that are in the foreground. And then we see some incredibly red galaxies that have been redshifted by the expansion of the universe itself. So this is pretty remarkable, but this is quite cosmic, it's quite abstract. And James Webb has not focused only on those abstract entities. We have focused even within our own solar system. So, as far as getting to the cool space stuff, I suggest that we start here in our solar system. Okay, it is 7:22 in the morning, but it's never too early to talk about space. So we're going to start here with this image of Jupiter. This is the Jupiter that we know and love, right? This is Jupiter in visible or optical light. So this is not an image taken by the James Webb Space Telescope. This is an image taken by Hubble. Because this is the Jupiter that we know and love, we see the familiar brown, orange, white stripes and the great red spot, as well as this interesting feature up here at the North Pole. Now this is actually the exact same phenomena as something that we experience on Earth at our North Pole. That is the northern lights, or the aurora. Those are high energy particles coming from the sun, interacting with Earth, or in this case Jupiter's magnetic field, warping down in towards the North Pole and causing that magnificent light. Now, one of my favorite things about this image in particular is these weird little dots with tails behind them. This is really peculiar, but what we're actually seeing here is the moons of Jupiter far out here interacting with Jupiter's magnetic field, looping back in, and that shadow being reflected on the aurora. So what does James Webb see when looking at Jupiter? Now, we're once again still looking at Jupiter, but it looks very different from the previous image. We can focus on different wavelengths, adjust the colors to bring out features that we want to focus on. And in this case, we're bringing out a few features in particular. One, we can notice the aurora are still visible at the North and South Pole, and even some glare has been brought out by the aurora, some haze. The details that this image are trying to pull out are found here, out on the edge of Jupiter. It kind of looks like a ring. That's because that's exactly what it is. Now, we often forget because Saturn has the most magnificent, most beautiful rings in our solar system, but in fact, all of the gas and ice giants have rings. That is to say, Jupiter, Saturn, Uranus, and Neptune all have ring systems. And in this case, the ring system is really brought out by this JWST image. So this is just one instance of JWST studying our solar system. There have been extensive studies on the rest of the planets, and there's a lot that we have learned. But I think that some of the more interesting stuff, arguably, is found when we go interstellar. When we go interstellar, we can start to look at things on larger scales. Okay, so listen, I'm not a stellar astrophysicist. What we're looking at here is the Orion Nebula as viewed by the Hubble Space Telescope. Now, if you actually go out and look at the Orion constellation in the night sky, below his belt, if you have a telescope or some binoculars, you can even see this nebula. So what is this? Well, this is where stars, that is to say solar systems, planets, come to be, live, and pass away. Our very own sun began in a nebula like this. Now, these nebulae tend to be found in the spiral arms of galaxies where there are starburst regions. That's where stars are coming to be, where there's lots of gas and dust and turbulence. This is where stars come from. Now, this is all governed by gravity in particular. Gravity is the thing that keeps our feet on the ground when we're walking around here on Earth. But out in space, gravity pulls things together. So when you have a giant cloud of gas and dust, like the Orion Nebula here, the gas will fall in on itself. If enough gas falls in on itself and begins to heat up and spin to the extent that nuclear fusion can begin, then you have a star. Nuclear fusion is like putting Lego bricks together. It's taking smaller elements and building them up to heavier elements. It is real-life alchemy. But this is just a Hubble image of the Orion Nebula. Next, we're going to look at a JWST image of a different nebula. This is another star-forming region, another stellar nursery, this time imaged by James Webb instead of by Hubble. So this means that now we're looking at a star-forming region in infrared light rather than in optical light. So we see some clear differences here, right? Instead of being blocked out by the gas and dust, the stars in the background here can actually peer through an infrared light. That heat is able to penetrate that gas and dust. This is where stars live their lives. This is where they come to be. And with the stars, planets form around them. This begs the question, what happens when a star dies? Stars don't live forever as much as they might seem to be eternal up in our night sky. They actually run out of fuel. Our own sun is due to run out of fuel in about 4.5 billion years. Our sun has already lived for about 4.5 billion years, but it has 4.5 billion years to go. That is to say, humanity is our sun's midlife crisis. Now, when our sun runs out of fuel, it'll start to expand out its outer layers, and then eventually it just lets those outer layers go out into space, creating what's called a planetary nebula. Left behind in the center is the skeleton of our sun, that is a white dwarf. But when massive stars, that is to say stars that are 8, 10, 20 times the mass of our sun, when they run out of fuel, something very different happens. I mentioned earlier that gravity dominates, and that applies here as well. When a massive star runs out of fuel, it'll puff out its outer layers in the same way that our sun did. It'll create what's called a red supergiant. These are some of the largest stars in the universe. And then it'll collapse back in on itself due to gravity and then explode in what's called a supernova. Now, these supernovae are some of the most energetic things in the universe. They create a lot of light and some very beautiful structures as well. This is one of those structures. This is a supernova remnant called the Crab Nebula. This particular image comes from Hubble, so this is it viewed in optical light, meaning it's essentially what we would see with our eyes. But this is what's left over from a massive star going supernova. Ran out of fuel, collapsed, exploded, released a ton of energy, left behind a neutron star at the center. This supernova remnant only became visible from Earth at about the year 1000, meaning that Pythagoras, in theory, if he had telescopes, would have looked up to a sky that didn't have this massive, extravagant nebula. That is to say, the sky changes, it just changes very slowly. Like I said, this is the Hubble image, so let's compare it to what James Webb saw. When we observe the same supernova remnant in infrared light, focusing on the heat of the structure instead of the light that we can see with our eyes, a very different story is told. In particular, I mentioned that neutron star at the center of the nebula. That is like the skeleton that's left behind. Neutron stars are stars that are more massive than the sun, but the size of cities. It's like the super dense skeleton that's left behind after the supermassive star explodes. Because neutron stars are so dense, just like a figure skater spinning more quickly when they tuck their arms in, neutron stars spin very, very quickly. When they spin very, very quickly, we call them pulsars. And that light can sometimes shoot around, and it creates some very interesting observations here on Earth. Now, we can actually see that when we're looking in infrared light. Here in the center of the image, we can see the waves thanks to the propagation from that spinning neutron star at the center. James Webb is unlocking new structures within this nebula that we didn't see previously. So this is a supernova remnant called Cassiopeia A, or Cas A. Once again, this is what's left behind by a supernova. You had a massive, massive star that ran out of fuel, expanded, collapsed, exploded, and left behind a neutron star at the center and released all of the gas out around the star. Now, if you remember, I was talking about nuclear fusion taking place in stars earlier. That means that at the beginning of the universe, we had the beginning building blocks, that is, mostly hydrogen and helium. Stars, like the Lego brick analogy, bring those elements together to create heavier elements. Some of these elements, like iron and oxygen, are crucial for how the world functions, how our body functions. The crucial ingredients in life were created in stars. Now, stars can only produce elements as heavy as iron. Beyond that, it takes too much energy for them to reasonably produce. That's where supernovae come in. Supernovae are incredibly energetic, and that explosion can create heavier elements like gold and silver, things like that. So, if you're wearing any silver or gold jewelry, know that the original metalsmith was an exploding giant star. Now, in this case, this exploding massive star left behind some very beautiful structures. In fact, the thing I want to focus on is down here in this bottom right corner. This is an epiphenomenon of this larger supernova remnant called Cassiopeia A. And in fact, it's about 170 light years behind this main supernova remnant. This is a good reminder that space is three-dimensional. When we get back this two-dimensional data, we actually have to interpret it to build a three-dimensional structure. In this case, baby Cassiopeia A is what's called a light echo that we can find behind the supernova remnant. This is a result of all of that energy from the supernova going out into space and heating up some distant gas, which then glows as it cools down. It glows in infrared light because as it's cooling down, it's radiating that heat in infrared light. So far, we have explored this data of James Webb in order of scale. So we started out with Jupiter within our own solar system. We looked at some interstellar objects. Now we're looking at supernova remnants. But everything we've considered so far, except for the deep field images that we started with, have taken place within our own galaxy. Our Milky Way galaxy is sort of like our cosmic neighborhood. It's the closest few 100 billion stars. But if we want to explore everything that James Webb has to offer, we have to go intergalactic. I have a tea problem. Galaxies are sort of like their own island universes. That's what Kant called them way back in the day. But what we now know is that they're really just gravitational collections of stars. So we live in our own Milky Way galaxy. That's the closest few 100 billion stars. The closest galaxy to us is the Andromeda galaxy, which has almost 1 trillion stars. And then there are trillions of other galaxies within our own observable universe. So this is one instance of that. Now, this is James Webb's second anniversary image. It is a galaxy merger known as ARP-142. It's more colloquially known as the Penguin Galaxy merger because you have this penguin galaxy shape due to the merger that's taking place, and then the little egg off to the side. Now, this merger began about 25 to 75 million years ago, and it will continue to merge for hundreds of millions of years. This is what this galaxy merger looked like when humanity started. This is what the galaxy merger looks like today. And this is what the galaxy merger will look like when humanity ends. This is the galaxy merger from humanity's perspective. We are frozen in time because our timescales are so much smaller than the timescales of these massive collisions. Now, once again, there's another interesting thing taking place here with scale and distance. So we see a two-dimensional image here, and we see 3 primary structures. But these 2 structures are interacting, and this one is actually 100 million light years closer to Earth than these 2. So this galaxy up in the top right-hand corner is really just photobombing. Sometimes gravity wins. That's become a theme in this video. In this case, gravity wins by two galaxies colliding with each other. Now, this is actually kind of a commonplace thing. It happens more often than we think it does. In fact, our own galaxy, the Milky Way, is due to collide with Andromeda in about 5 billion years. So don't hold your breath. What's wild about these galaxy mergers is that when they collide, it's kind of like two ghosts trying to high five. These galaxies are filled with billions of stars, hundreds of billions often, but because space is so ginormous and because stars are so small relative to the scales of the galaxies, when they collide, it's kind of just a gravitational dance. Nothing actually collides. If you were to stay on Earth in 5 billion years, when Andromeda takes place, that is the combination of the Milky Way and Andromeda, you would be fine. You could stand on Earth and watch the whole thing take place, no problem. There may very well be creatures witnessing this galaxy merger take place from within the galaxy. Okay, so let's pause for a moment to think about where we've come from and where we're going. At the very beginning of this video, I mentioned that the purpose of the Webb Space Telescope is to study our origins and the universe. That's the most fundamental version of what James Webb is here to do. So far, we've covered a lot. We've covered objects within our own solar system, we've covered interstellar objects, and we've covered intergalactic objects. Fundamentally, if we want to study our origins, we have to enter the realm of cosmology. And this is where physicists and theologians have more in common than they want to admit. This is where we're studying the origins of our own universe. Part of the reason why James Webb observes in infrared light is because of the expansion of the universe causing the stretching of light into longer and longer wavelengths. Infrared light is a very, very good wavelength of light to focus on if we want to study structures in the early universe. James Webb, with its massive mirror and the pinnacle of astronomical observation technology, peered back as far as we can right now. Now, what cosmologists expected to discover in the early universe were few small galaxies. If you think about it, if the universe had only existed for a few 100 million years, there should be very few galaxies and they should be relatively small. There simply hadn't been enough time yet to create large structures. When we used this pinnacle of observation technology to look further and further back in the universe, that's not what we found. We found way too many galaxies that are way too large to explain. And this is where science writers fail us. This is where science journalists tend to blow things out of proportion and they say, James Webb has broken cosmology. That's not true, and that's what I'm going to explain now. Good science means interpreting the data that we collect and then trying to model it to best represent the universe that we find ourselves in. That means that when we use James Webb to look back into the early universe and we see things that we don't expect, we don't give up on our current cosmological model. Instead, we try to adapt it. We try to figure out where we went wrong. And in this case, as I mentioned, we saw way too many galaxies and we saw way too many massive galaxies in particular. Now, cosmologists have been studying this a lot over the past 2 years. And what they've discovered is that the extra mass can be accounted for by something called quasars. At the center of some galaxies, there are black holes that are actively accreting mass. When they're actively accreting that gas and dust, it heats up a lot because it's falling into a literal pit in space-time. When it heats up that much, it creates a lot of energy that can be incredibly bright. These are some of the brightest objects in the universe. Now, when you're looking back far into the early parts of the universe and you see something that's very bright, that can make it seem like it's a lot more massive than it actually is. So that's one possible explanation for the additional mass that we see. Regarding the fact that there are twice as many galaxies as we expected, that might be explained by the fact that the universe was so much denser at the beginning of the universe. Perhaps it was easier to create galaxies when the universe was denser 300 million years after the Big Bang rather than 13.8 billion years after the Big Bang, where we find ourselves now. So I bring all of this up to really stress that James Webb is remarkable. It has taught us so much about the universe and our origins, and it will continue to do so for years to come. But that doesn't mean that we've discovered alien life or that we've broken our modern cosmological model. But rather, it's been quite the opposite. What we've learned using the Webb telescope has only added to what we currently know and solidified and built upon and improved our current models. We haven't discovered alien life, but we've found trace gases that could be explained by alien life. We haven't broken modern cosmology, but we have explained new ways to perhaps interpret why there are so many galaxies in the early universe. This tradition of studying the universe and our origins is uniquely Homo sapien. In this video, I've covered that story, starting with Pythagoras, a little bit strangely, through to modern Europe with Galileo and Kepler, and eventually landing on us. We are here now with this current pinnacle of astronomical observation technology, where we get to use the Webb Space Telescope to peer back into some of the earliest moments of the universe. In continuing to develop this technology, we will be able to continue to peer further and further back. It will be an amazing thing to watch play out. For the time being, we are a continuation of our human tradition of studying ourselves and the universe, and James Webb has been a beautiful and important tool in aiding that discovery.